Hello everybody, welcome into another lesson. So today we are going to talk about limits at infinity, not to be confused with infinite limits. Limits at infinity actually denote taking the limit as x approaches infinity or negative infinity of a function, whereas infinite limits are when you get infinity or negative infinity for your answer. So that's the difference. So today are limits at infinity. Now we're going to start out with the degree of the numerator less than that of the denominator. Then we'll move into the degree of the numerator equal to the degree of the denominator. Then we'll do the degree of the numerator greater than the degree of the denominator, and then we'll even do some radical functions, and we'll do some polynomial functions. So let's go ahead and get started here. So you have the limit as x approaches infinity of 1 over 2x plus 3. We notice the degree of the numerator is less than that of the denominator. Well, that 1, you could think of that as 1 times x to the 0, because x to the 0 will give you a constant. So that means then that since the degree of the numerator is less than that of the denominator, that means that the denominator is increasing faster than the numerator. So if I put in any value of x, and I keep going up and up and up, what's going to happen is I'm going to get 1 divided by a really large number, and it's going to keep happening until eventually I get a decimal number really close to 0. In fact, the limit in this case would be 0. And this is true for any time you have the degree of the numerator less than that of the denominator. If you have a limit as x approaches infinity or negative infinity of a function like that, the limit will always be 0. Now, why don't we go ahead real quick and let's take the limit as x approaches negative infinity of this function. So the limit as x approaches negative infinity of this exact same function, well, I put in any number in the denominator, since it's increasing faster than the numerator, any very large negative number, I'm going to get a negative decimal number incredibly close to 0. So the limit in this case would also be 0. So if the degree of the numerator is less than that of the denominator, whether you're taking the limit as x approaches positive infinity or negative infinity, the answer is always 0. And another thing about limits at infinity is that obviously we can't have one-sided limits for that, because infinity is undefined. Whether we approach from the left or right, we can't define it. So you're just taking the general limit for infinity or negative infinity. That's all you can really do. Let's do one more where you have the degree the degree of the numerator less than the denominator. Let's take the limit as t approaches negative infinity of t squared plus 2 all over t cubed plus t squared minus 1. So we have the limit as t approaches negative infinity of t squared plus 2 all over t cubed plus t squared minus 1. Well, notice the degree of the numerator is less than that of the denominator, so by default the limit's going to be 0. We don't even have to do anything with it. The limit is going to be 0. Simple enough. Now where it changes a bit is when you get into what we're about to do next is when the degree of the numerator is the same as the degree of the denominator. So let's do some of those. So we have the limit as x approaches infinity of 3x squared minus x plus 4 divided by 2x squared plus 5x minus 8. Alright, so we have the limit as x approaches infinity of 3x squared minus x plus 4 divided by 2x squared plus 5x minus 8. Okay, so the degree of the numerator is the same as the degree of the denominator. What you have to do whenever you have a limit to infinity or negative infinity where the degree of the numerator equals the degree of the denominator is you look for the leading coefficient in each numerator and denominator, which of course, as we know from algebra, is the coefficient of the highest power term. And then we don't even care about the other terms in each, we only care about the highest power. And all you have to do to find that limit is take the ratio of the two leading coefficients, which in this case would give you a limit of 3/2. So the ratio of the leading coefficients is 3/2, and that is your limit as x approaches infinity. It would give you 3/2. Now, let's say we take x to negative infinity. This time, let's take the limit as x approaches negative infinity. In fact, you know what? Let me up the ante here. What if I made the leading powers, what if I made the power on each to the third power? So let's take the limit as x approaches negative infinity of 3x to the third minus x plus 4 over 2x to the third plus 5x minus 8. Well, we're going to negative infinity this time. Now, the degree of the numerator and denominator are equal in the fact that they're both to the third power. Well, here's the thing. If I put in a negative number for the third power, I get a negative number, right? But it would also happen in the denominator, which would mean you're dividing a negative by a negative, which would actually turn it into a positive. So what this means is if the degree of the numerator equals the degree of the denominator, it doesn't matter if you're approaching positive infinity or negative infinity, the answer to the limit is always the ratio of the two leading coefficients, which would still give you positive 3/2. So the limit in this case would still be 3/2, even though we're going towards negative infinity. And that rule applies if the degree of the numerator and denominator are the same power. Let's see. The limit as x approaches infinity of 3x plus 5 all over x plus 4. So we're going to take the limit as x approaches infinity of 3x plus 5 all over x plus 4. Well, notice the degree of the numerator equals the degree of the denominator. Well, we're going to take the ratio of the leading coefficients, which would be 3 to 1, which would just be 3. So the limit in this case would be 3. That one's easy enough. Now, what if I gave you something like this? So the limit as x approaches infinity of the square root of 12x cubed minus 5x plus 2 all over 1 plus 4x squared plus 3x cubed. So now we have the limit as x approaches infinity of the square root of 12x cubed minus 5x plus 2 divided by 1 plus 4x squared plus 3x cubed. One thing to keep in mind is that your leading coefficients are not always in order. Sometimes you'll go from descending order, and then sometimes you'll go into ascending order. Just watch out for your leading coefficients. But both numerator and denominator have equal degree, so it's going to be the ratio, of course, of the coefficients, but we have to bear in mind the square root sign. So this is going to equal the square root of 12 divided by 3, which would end up giving you the square root of 4, which would actually make your limit in this case 2. So always remember to take your square root signs, and that'll give you a limit of 2. Let's see, the limit as y approaches infinity of 2 minus 3y squared divided by 5y squared plus 4y. So the limit as y approaches infinity of 2 minus 3y squared all over 5y squared plus 4y, well, both numerator and denominator of equal degree, they're both to the second power, so this is just going to be the ratio of the leading coefficients, which would end up giving you negative 3/5. So this limit would end up being negative 3/5. Alright, now what if I have something like this? The limit as u approaches infinity of 4u to the 4th plus 5 divided by the quantity of u squared minus 2 times 2u squared minus 1. So this time the denominator is split up into two factors of quadratic terms. The numerator is raised to the 4th power. Well, good news is we don't have to go through all this FOILing in the denominator. If you just multiply the two first terms of each quantity in the denominator, you would get 2u to the 4th. So you end up then having that the numerator and denominator are of equal degree, so you could take the ratio of the leading coefficients, which would be 4 over 2, since you would end up getting 2u to the 4th in the denominator. Well, 4 divided by 2 is 2. So the limit in this case would end up being 2. So also look out for ones that are factored like that, because at first glance it may have looked like the degree of the numerator was higher than the denominator when it really wasn't. Alright, now let's take the limit as x approaches infinity of the square root of 9x to the 6th minus x divided by x cubed plus 1. So we have the limit as x approaches infinity of the square root of 9x to the 6th minus x divided by x cubed plus 1. And at first glance it might look like the degree of the numerator is greater than that of the denominator, But let's really look at the numerator. If I take the square root of 9x to the 6th, that would end up giving me 3x to the 3rd, right? So in actuality, these are the same degree in the numerator and denominator. So that means you just take the ratio of the leading coefficients, that'd be 3 to 1, or simply 3. So the limit in this case would be 3. Now let's take this same function, the limit as x approaches negative infinity of this exact same function, 9x to the 6th minus x all over x cubed plus 1. Well, we've already determined that in the numerator, the square root of 9x to the 6th is 3x to the 3rd, which would actually, again, give you equal degrees for the numerator and denominator. So it's just going to be the ratio of the leading coefficients, which is also 3. So either way, towards positive infinity or negative infinity, you get a limit of 3. Alright, so I think that's good enough for the numerator equal to the denominator. Now let's go on to when the numerator is greater than the denominator. That changes everything. So let me just find one. All right, the limit as x approaches infinity of x to the 3rd minus 2x plus 3 divided by 5 minus 2x squared. Alright, so we have the limit as x approaches infinity of x to the 3rd minus 2x plus 3 all over 5 minus 2x squared. Well, if you notice, the highest degree of the denominator is 2, the highest degree of the numerator is 3, so the degree of the numerator is greater than that of the denominator. So what does that mean? That means that the numerator is increasing faster than the denominator. So if I put in any value of x and it keeps going up and up and up, it's definitely going to increase faster for that value to the 3rd power over to the 2nd power. That means eventually you're going to get to infinity. It just keeps going up and up and up. So in this case, the limit as x approaches infinity of this function would be positive infinity. That would be the value of your limit. Now, what if we take the same function, we take the limit as x approaches negative infinity of this exact same function. So x to the 3rd minus 2x plus 3 all over 5 minus 2x squared. Well, again, the degree of the numerator is greater than that of the degree of the denominator. That means that the numerator is increasing faster than the denominator. But if I take any high negative value to the 3rd power, well, I'm just going to get a negative answer because a negative to the 3rd power is a negative. So my limit in this case would become negative infinity, since my limit is going towards negative infinity. Well, now let's change this a minute here. I think we can see that because the numerator has a degree of 3 on each of these, that's why the limits are positive and negative respectively. What if I decrease the degree by 1? So in this case, let's say I make it Now I'm going to take the limit as x approaches positive infinity of x squared minus 2x plus 3 all over 5 minus 2x. Well, the degree of the numerator is still greater than the denominator, and if I put in any value to the second power, then it's increasing faster than the first power, so my limit as x approaches infinity is infinity. Now let's do that same function with the limit approaching negative infinity. Now, of course, if I take any negative number and I raise it to the second power, it's going to be positive. So in this case, my limit as x approaches negative infinity actually ends up being positive infinity. It's all based on your sign and your power. You have to really make sure you look at the sign and the power of what you're raising this to. That'll help you determine your limit. Let's do one more. And then we're going to move into some radical functions. Alright, so we have the limit as x approaches infinity of x plus x to the third plus x to the fifth, all that divided by 1 minus x squared plus x to the fourth. So we're going to take the limit as x approaches infinity of x plus x to the third plus x to the fifth, all divided by 1 minus x squared plus x to the fourth. Well, the degree of the numerator is 5, degree of the numerator is 4, so very clearly the degree of the numerator is greater than that of the denominator. That means then that this limit is going to go to infinity. So the limit in this case would be infinity. Alright, so those are examples of numerator to higher power than denominator. Now, let's do some other types here. Let's say I give you some radicals. Let's start out real easy on some radical functions. The limit as x approaches infinity of the square root of x. This is almost laughable, because if you look at the graph of the square root of x, well, you still keep going up and up and up and up in your x values. You're still going higher and higher in your y values, just at a slower rate, but it's still going to be infinity. So the limit in this case as x approaches infinity of the square root of x is infinity. Now, let's take the limit as x approaches negative infinity of the square root of x. Well, right away we have a problem. The square root function, or any even root function for that matter, is not defined for any values less than 0. So right away this limit does not exist, because you cannot have a negative value under a square root sign or any even root sign. Now let's change this a little bit here. What if I took, this time we'll do the cube root function. So the limit as x approaches infinity of the cube root of x, well, that should be easy. Your limit's still going to be infinity. Now, what about as x approaches negative infinity of the cube root of x? The good news is for the cube root function, or for any odd root function, it is defined for the set of all real numbers. So the cube root of a negative number is going to give you a negative. That means that the limit as x approaches negative infinity of the cube root of x would be negative infinity. Alright, those are easy enough. You're like, why do we even bother with those? Well, let me show you one example here of why we bother. Let's say I have the limit as you have something like 9x squared, square root of 9x squared plus x, all that minus 3x. Well, what are we going to do then? We don't have denominators, we just have square root minus a regular polynomial term. What are we going to do then? Well, the square root of 9x squared would be 3x, right? Technically 3 times the absolute value of x, but it's going to be 3x since we're approaching positive infinity, so we'll just say it's 3x. But you would still have the square root of x to deal with in there, so basically what would happen is you would end up getting something like infinity minus infinity, which I know a lot of you are going to rush and say 0. This is false. It does not equal 0. The reason being is because infinity itself isn't defined. So how can we say what infinity is and then say it's equal to 0 when we subtract itself from it? Well, this is actually an indeterminate form, which once we learn derivatives really well, we're going to use a method called L'Hospital's rule to help us deal with indeterminate forms. But for now, we don't have that just yet. So how are we going to remedy this? Well, it goes back to when we did limits earlier in the course. We can still use the conjugate method. So let's go ahead and break out the conjugate method. So let's take the limit as x approaches infinity, and then let's form the conjugate. So this would be the square root of 9x squared plus x minus that 3x, then multiply the numerator and denominator by its conjugate, which would be the square root of 9x squared plus x plus 3x all over the square root of 9x squared plus x, then plus the 3x. Let's simplify this a bit. This would turn into the limit as x approaches infinity of, now you FOIL out your numerator, it ends up simplifying into 9x squared plus x minus 9x squared all over the square root of 9x squared plus x plus 3x. Well, the numerator will simplify one step further. This is going to turn into the limit as x approaches infinity of x all over the square root of 9x squared plus x, then plus that extra 3x. And it might look like the degree of the denominator is greater than the numerator, but that's actually not so. What's the square root of 9x squared? It's 3x, right? It's going to be positive. It's going to be 3 times positive x simply for the fact that we're approaching positive infinity. So you take the square root of 9x squared, you get 3x. You would actually then have 2 first power terms in your denominator and 1 in your numerator. Well, that means the numerator degree equals that of the denominator. So you're going to take the ratio of the leading coefficients. So the numerator, of course, is 1, but in the denominator, the square root of 9x squared, that's 3x. So you'll have 2 leading coefficients. You'll have 3 plus 3. Take their sum, you actually end up getting a limit of 1/6. So the limit in this case is actually 1/6. I know it looked indeterminate at first, but using the conjugate method, you get 1/6. Now, I do want to do one polynomial example. So let's go ahead and do that. Technically, it's 1 split into 2 pieces, but let's say you have the limit as x approaches infinity of the quantity of x to the 4th minus x to the 5th. Alright, so what do we got here? The limit as x approaches infinity of x to the 4th minus x to the 5th. Well, this is going to look a lot like infinity minus infinity. That rule, however, only applied if they were both to the same power. It doesn't apply then. I mean, it only applies then. This is different in the fact of one thing. You have both x to the 4th and x to the 5th. Let's take any number to the 4th power, and then take that same number, raise it to the 5th power. Obviously, the 5th power is going to win, right? Well, I keep going up and up and up and up. Let's say, oh heck, let's say I take 2 to the 4th. What does that give me? That gives me 16. Then I take 2 to the 5th, I get 32. This time I'll take 3 to the 4th, that would give me 81. Then I end up taking, let's see here, 3 to the 5th, I end up getting 243. I take 10 to the 4th, I end up getting 10,000. I take 10 to the 5th, I get 100,000. You see where I'm going with this? The greater the number is, the higher and higher you get, the greater the gap between your values to the 4th power and the 5th power. And obviously the number is going to increase faster when it goes to the 5th power as opposed to the 4th power. So the point I'm trying to drive home here is that you're taking some number minus an even bigger number, and you're going to keep coming up and up and up to where you're going to get so large and negative you actually go towards negative infinity. So in this case, the actual limit would end up being negative infinity. Simply for the fact that x to the 5th increases faster than x to the 4th. Now, let's modify this a little bit. Let's say I make this x to the 4th plus x to the 5th, but I'm going to take the limit as x approaches negative infinity of that function. So the limit as x approaches negative infinity of x to the 4th plus x to the 5th. Well, again, x to the 5th is definitely increasing faster than x to the 4th. Had we been taking the limit of positive infinity, the limit as we go to positive infinity, it would actually be undefined, because then you would have infinity plus infinity. We can't define that. But having said that x to the 5th increases faster than x to the 4th, what is true about if we put in any negative number to the 4th power? It's going to be positive. And if we put in that same negative number but we raise it to the 5th power, you're going to get an even bigger negative number. So actually what's going to happen is your limit is also going to go to negative infinity in this case, because x to the 5th is bigger and you're actually getting more increasingly negative. So you would also get a limit of negative infinity. Alright, so that's it for this lesson. The next lesson we'll get into some special types of functions like some rational logarithmic, some trig functions, inverse trig functions, some rational exponential functions, so on. We'll find limits at infinity for those. So I hope everybody has a great day. Take care.